We made a water filter project.
And the question is, will the water be dirty or clean?
And then the hypothesis was we predict that the water would be a little yellow and not be drinkable. The materials are a big plastic bottle, cotton, rocks, dirty water, scissors, sand, rubber bands, pebbles, towels, paper towels, and felt.
And the instructions are, first you cut the bottle into pieces and you put the materials in the plastic bottle and then you put the dirty water in the filter.
The results were our hypothesis was right. The water was a little yellow and was not drinkable. The conclusion, the water was dirty because it wasn't a real filter, but the project was still fun.
And here are some pictures that we did by Raina,
Yarina, and Liliana.
So here we have the Better Together project by Isla and Cora Mobley, and we are showing how we grew these 3 plants, one with oregano and basil packet, one just basil alone, and one with 2 packs of basil. And together they all tried to compete and grew better together. But the one that grew first and was doing best was the basil and oregano. And then the other one started growing later on. For our materials, we used indoor planting soil, then basil seeds, oregano seeds, planting labels, and draining pots. And over here we have just a data collected chart with how high, the dark green is how many days it took to grow, and the light green is the size of the shoots, aka the little plants right here. You can actually come and see them right there. And our scientific question was, do plants grow better when they are alone or when they are with their friends? And our hypothesis was we thought that they were going to grow better alone because they could have been trying to compete, and the other one was like taking all the soil or too much sunlight while the other one wasn't getting enough. But in conclusion, we were wrong, and they grew better with friends. But we didn't know if it was because of competition or if it was because they were just had friends, like how people like get raised better when they are when they have friends. Like if you feel more comfortable when you have your friend or pal with you, but when you're alone, you don't feel that as confident. While on the other hand, they could have just been competing and one over the other. But everything turned out well in the end, and the sprouts went pretty high, and we're going to try and see how much longer they could keep up. Thank you.
Tell us what you did and what you found.
So first we put the food out in a boiler room, and we waited 2 weeks, and then 3 weeks, and then we saw which food grew the mold, and then this is the beginning of it, and this is the end. This is the food chosen.
So clearly the egg didn't grow mold, but it just like drifted apart, and this all the juice got out of it.
Which one is that? What is that?
This is a strawberry.
A strawberry, okay.
This is
Can I ask what started? Why did you want to grow mold? What was your inspiration for your project?
Well, like
we just thought it would be interesting,
and like
see
see
what would
like
happen.
why you don't want to leave your food out. Which ones like do you not want to leave out your food the longest?
Okay.
So did you think there was a characteristic of those that got moldy versus those that didn't? Was there something about it that you think made it get moldy?
We really thought the bread was gonna get mold.
We thought also the one that was the most like moist would also get a lot of mold, because that's where mold grows around most.
Okay.
And that's like also why we put it in the boiling room, because like hotness
Yeah. So is that what you found? I'm sorry, go ahead. No?
And it was moist in the boiler room, so we thought it would grow mold in there.
And so was your hypothesis right that the moistest ones
Yeah.
would be the ones that
Yeah,
molded
but
the
we
most?
didn't get the what we thought would do it. We really thought the bread, but I think it was because of the type of bread that really made it.
Okay, so
like-
you think another type of bread would have made a
Grew
little bit
mold.
more? Like what
Yeah.
type?
I don't really know which we did, but I think like a different type of bread wouldn't grow mold faster.
Like maybe sourdough or something.
Yeah, something that has like lots of moist in it. This one was just like a dry piece of bread.
Okay. What did you keep? What did you not experiment on? You had a control, right?
Yeah,
Something-
our control was that they're all in plastic containers that are in dark and hot room for 3 weeks.
Okay. And is this your data? Where's your data? This
Yeah.
is what you collected, or that's okay? The time. I see it. I see
So
it.
how did you measure how much mold they have?
So we took pictures of them when they didn't have mold, and then when they did have mold, and then this one in 2 days the strawberry grew mold. That was very fast
That
for
was the
us.
fastest.
And then this 2/3 of the cheese grew mold, but I think it was like 6 or 7 days out.
Okay. So did you keep track of when they grew mold for each product?
Yeah, we took it in my notebook. Yeah.
Okay, great. Did you girls have a nice time doing this?
Yeah,
Have
that was
fun?
fun.
How many weights do you think each object can hold before breaking? When we say a number, it means these. We used Lego gumballs as weights to test the strength. Zoe thought the hypothesis was 12 for the cheer string. Olivia thought the hypothesis was 10 for the cheer string. Violet thought the hypothesis was 11 for the cheer string. Who do you think was the closest to the right answer?
Can I see that? What do you think? Guess. 1 through 16.
11. Oh, 10.
So you think 11?
And I guessed the right answer.
Now let me 16. I got the closest. Now, fun fact: hair is electric.
Yeah, nice fun fact.
Nice fun facts. Now,
Here, take the.
yes.
Zoe thought the hypothesis was 4 for tissue. Olivia thought the hypothesis was 16 max for tissue. Violet thought the hypothesis was 8 for tissue. Who do you think was the closest to the right answer? Max 16 was the right answer. Olivia was the closest. What do you think koosh ball strand is? What do you think koosh ball strand is? Oh, Zoe thought the hypothesis was 5. Violet thought the hypothesis was 4. Olivia thought the hypothesis was 5. Who do you think got the closest? The answer for the koosh ball was 12. Olivia and Zoe got the closest. This is hair under the microscope. This is hair with color under the microscope.
And that is our presentation.
Yeah, that is our presentation.
Oh, and this is.
that proves that hair is the least strongest out of all of these.
And hairspray makes it stronger.
And hairspray makes it stronger. The effects on water temperature on elephants' toothpaste. Try 1. Water temperature is 3.59 degrees. Speed of reaction is 2.5 seconds to the top of the bottle. Amount of foam, heavy. Movement of foam, thick even coat around the entire bottle. Other observations, a little clumpy, drippy. Trial 2, green. Water temperature 69.4 degrees. Speed of reaction 3.5 seconds to the top of the ball. Amount of foam, medium. Movement of foam, shoots out of bottle, streams down the side. Other observations, reacts ended quickly. Trial 3, yellow. Water temperature 126.9 degrees. Speed of reaction 4 seconds to the top of a ball. Amount of foam, medium. Movement of foam, twisted around the bottle. Other observations, look like soft serve ice cream. Trial 4, water temperature 150.6 degrees, speed of reaction 4 seconds to top of bottle, amount of foam, heavy, movement of foam, thick, even coat around entire bottle, all our observations. Reactions lasted a long time. Materials: yeast 1 tablespoon, hydrogen peroxide a half a cup, soap 1 squirt, water 3 tablespoons, food coloring 9 drops. And these are all the ingredients. And then the results, I did a graph and it tells you the speed of reaction and the temperature. And for this one, the temperature was 35. And then it went up for each reaction, and it took 4 seconds for the biggest one.
Our hypothesis was we think after 30 minutes the salt will damage the slime most out of the toothpaste and the Sprite.
The salt will damage the slime the most, more than the toothpaste and the spray.
Yeah.
Okay. So tell me how you set up your project.
So our process was
Number 1, we made the activator with borax and water.
So what is the activator? That's the container that has the.
So it's like
this, it activates the slime to turn it into a slime.
because then it would just be glue.
Okay. So you're making slime.
Yeah.
Okay.
And then
Step 2, pour the glue into 3 containers.
Step 3.
So now you're gonna have 3 containers of slime.
because we're comparing.
And step 3.
Pour the activator into the 3 bowls of glue.
Put Sprite, toothpaste, and salt into 3 bowls.
So one of them into each.
Yeah.
Step 5, wait 30 minutes.
Step 6, see what the reaction it made.
And then we're all done. So this is our before,
This one's the toothpaste, that's the salt, and then that's the Sprite.
but then here are the ingredients we used.
Yeah.
We used 3 containers,
Salt,
Sprite, toothpaste,
Sprite.
borax,
glue.
So this was
Water.
the
This was
toothpaste one.
toothpaste.
it made it just a little, since the glue made it
This
very
is all dried
liquid.
up in the Sprite, right?
Yeah, it's like liquidy too.
And this.
And that was
This
just
is-
raw.
It's rock hard.
You can't play
The
with
salt
it.
like took out the water.
Yeah.
What was your hypothesis?
That was our.
Salt will damage the slime the most.
And it
then
did.
This is our conclusion.
We were right. After 30 minutes, the salt damaged the slime the most. The salt took out the water of the slime, so it was just a big chunky ball. The Sprite made the slime softer, stretchier, and crunchier. Also, the toothpaste made the slime chunky and also scented it.
The reason why these don't look like that is because we had these sitting out a while because we
Okay. Right, I see.
But for 30 minutes, it was that.
it was like that.
So salt, now you learned a lot about salt, right?
Yeah.
It dries things out,
It's
doesn't
very powerful.
it? Takes
So
water.
now we know not to put this, and we also know we can put Sprite and slime
Just
because
don't leave it in there for a while.
yeah,
Don't leave it where?
in
In
the
the like don't
container.
leave like after a couple minutes, just
And
drain it out so
I
it
think
won't, like,
toothpaste was like a middle option to play with because
Yeah.
we don't fully know how
It's not really stretchy, but like it's fine
like-
to play with.
Yeah,
Like,
yeah.
it's not that bad.
It also made it a little chunky.
Yeah.
But we think this the Sprite did the least damage.
Right to the least damage. Okay.
And then these are our after results. That's how it looked before they all melted.
And we also put some clay in the slimes to make it colorful,
and it
it
made it more soft.
Oh, okay.
We used it to make it.
we
But it
and
all
we just brought
impacted them the
toothpaste.
same, right?
Yeah, we made that like presentable and fun.
That's the before.
This is the before.
yeah.
So they're all kind of the same.
Yeah. We just added some confetti.
Very colorful. Very
And
nice.
that's our project.
Okay, excellent. All right.
The question was which salt melts and ice snow the best. Hypothesis: I think table morn salt will melt the snow and ice the best. Procedure: first, I put snow and ice into 4 different pans and bowls. Then I added salt to each container. Then I measure how much snow and ice remained at 0 hours, 2 hours, and 4 hours and 18 hours. 5 equals the most snow and ice. zero equals the least known ice. This my data and my hypothesis was incorrect because ice melts is gone down to 0 and 1. And the control is all 5 because we did not put any salt on it. And it was below 15 degrees Fahrenheit. Conclusion. My hypothesis was incorrect. Salt B was the best at melting the snow and ice. To measure snow and ice, use salt B, which is ice melt.
So this was the Taste the Rainbow experiment. So we had to we had a blindfold on and we had to taste different flavors of gummy bears. And we found out that each gummy bear, some had different flavors, but other tasted the same. But when you see the color of the gummy bear, it tastes like that flavor. So your taste sends a signal to your eyes send a signal to your brain that it's gonna taste like that flavor, and it affects how you taste it. So my introduction was, does our sight affect our taste? My hypothesis was, I think our sight affects our taste because our eyes send signals to our brain telling us what to expect before we eat it. And I did some research on the official website of the gummy haribo.com, and then we learned on this YouTube video that our brain gets information from our 5 senses: smell, touch, and taste, and hear, and sight. And some of our senses rely on each other. And our materials was 1 blindfold, gummy bears, each flavor, 2 mini bowls, a pencil, a paper, and then we had water so we could drink after we eat the gummy bear, and then we have human participants. So this is what we did. We picked 1 gummy bear from each flavor in a bowl, total of 5. Without a blindfold, taste each gummy bear so we see what color and taste each flavor. Then blindfold the first taste tester. The other person will record the results. 1 by 1, the blindfold taste tester will try all gummy bears and say what flavor they think they are, drinking water in between. The other person will record their guesses to see if they match. Switch and repeat the same process for the other persons to gather results to compare. So this was our data, it was matching. And then our results is, I guessed when the flavor was raspberry, I guessed strawberry. When I guessed orange, I guessed orange. When it was lemon, I guessed pineapple. And when it was pineapple, I guessed lemon. What was given, this is the second one. She guessed raspberry, she guessed orange. The flavor was lemon, but she thought it was pineapple. It was strawberry, she thought strawberry, and then it was pineapple, but she thought lemon. And then conclusion, as a result, my hypothesis was true. When I saw the color of the gummy bear, I knew what the taste was going to be like. It food my eyes sent a signal to my brain telling me what the flavor was. When I was blindfolded, I tasted a different flavor than the matching color of the gummy bear.
So this is my project. It's a catching wind, finding the best blade angle. So this is where my background is. Wind power uses moving air to make clean energy. The sun heats the earth, and this makes wind. The wind spins the blades on a wind turbine. The spinning blades turn a generator to make electricity for our homes. Wind power is good because it does not cause pollution. Wind turbines work best when the blades are at a small angle, about 10 to 20 degrees. If the wind is slow, the blades tilt to catch more air. If the wind is very fast, the blades turn flatter to stay safe. A small angle helps the blades spin faster. And then my hypothesis is, if I set the blades at a small angle to 10 to 20 degrees, then the turbine will spin the fastest and make the most electricity. I think this will happen because the blades will catch the wind just right. Use a protractor to set the blades at 0 degrees. Turn on the fan. the fan. Look at the light bulb and see how bright it is. Write down what you see. Repeat the steps with 20, 45, and 90 degrees. Then my results are the blade set at 20 degrees made the light bulb shine the brightest. This angle helped the blades catch the most wind and spin well. At 0 degrees, the blades were too flat and did not catch enough wind. At 45 and 90 degrees, the blades were too steep and the wind slowed them down. This shows that the right blade angle helps wind turbines make the most electricity. Wind power is a clean way to make energy and helps keep our planet safe. So this is the 0 degrees, it didn't light up at all. This is the 20 degrees, it light up a lot. This is the 45, and this is the 90. And then this is where I got all of my information from. And then if I turn on the fan, so it's not really lighting up. And then for the 20, let me try the 90. This one shouldn't be turning on at all. Yeah. This one's right. So that's the 90. Hypothesis is that the boat will move as soon as the toothpick with the dishwashing liquid touches the water. We think this because once the water molecules cling together, they will pull the boat in different directions. Problem and solution. When we first started, we used squares at the end of the boat, but that didn't turn out so well. Then we learned that a triangle would be a better shape, so we made a triangle and it worked out better. If the water gets too soapy, the project will not work. So you would have to change the water in order to do this experiment. Results. The triangle shape did work better than the square, and every time we did it, we had to change up the water and wipe down our toothpick. Then the boat successfully moved when we did those two things. Conclusion. In conclusion, our experiment was successful due to the surface tension and invisible forces pulling the water molecules together. The dishwashing liquid weakens the bonds between the water molecules and pushes the boat easily throughout the water. Method. There are many different methods doing this project. Like we did a square and then a triangle, and at the end of the boat, you can even make a boat a circle. You could have many different ideas for this project. Then you can test them out, which design supports the boat the most. Here are some examples. Materials. Items. Toothpick, scissors, colored card, white card, dishwashing liquid, tray with water, paint, and paintbrush. We did static electricity, and we used balloons, soda cans, and paper to see which one sticks to the wall more and has the most friction. We thought that the balloon would work the best, and it did. We thought the paper would work the second best, and so it came would work hardly, and we were correct, so our hypothesis was correct. Yeah. And when we stuck the balloons to the wall and stuff, only her, when she rubbed the balloon on her hair, hers was the only one that stayed on the wall, and ours didn't. And we noticed that it was the only one that stuck to the wall between the paper and the soda can. It turned out we thought that my hair probably worked the best because I don't use that many hair products, and they use hair products quite frequently. I don't use hair products, I just wash my hair, brush it, but turns out that my hair had the most friction because the balloon lasted 35 minutes, 45 seconds, and 25 milliseconds. And the paper lasted 1 second and the soda and 3 milliseconds. And the soda can lasted 40 milliseconds. I think that's it.
This is the egg drop project. We did we did what home objects protect the egg the best?
We did aluminum foil, did not crack the egg. A Ziploc bag, didn't crack the egg. A Ziploc bag with paper towels, didn't crack the egg. Bubble wrapped, the ends were taped, did not crack the egg. 4 layers of air pockets that cracked the egg. 2 thin sponges did not crack the egg. 2 thin sponges in a shoebox did not crack. 2 thick sponges cracked the egg. Thin sponge wrapped in air pockets did not crack the egg. A thin sponge with bubble wrap did not crack the egg. A cup cracked the egg. A cup with cotton balls did not crack the egg. A cup with 1 sponge, cotton balls, and Easter grass did not crack the eggs. A plastic jar cracked the egg. A plastic jar with cotton balls cracked the egg. A plastic jar of water did not crack the egg.
Plastic jar with cotton ball air pockets did not crack. Plastic jar with cotton balls and bubble wrap did not. Plastic jar with cotton ball and bubble wraps cracked.
The plastic case cracked the egg, and Easter eggs with Easter grass cracked the egg. We did an experiment design per steer. We took turns deciding what to use to protect each egg. The eggs were dropped from 5.2 feet. They were dropped onto a wood floor with a tablecloth, so there was no mess. In conclusion, there are many ways to protect the egg from not cracking. Some objects will protect the egg, but some will not protect the egg. For example, a couple of cotton balls will not crack the egg. A plastic jar will not protect the egg without water. Most of the objects that protected the egg had more padding and more air around them. Air, liquid, and extra padding protect the shell from cracking when hitting the wood floor.
Thank you.
So we did our title is Breaking the Freeze, the role of salt in bonding a match to ice. So what we did was we took a cup of cold water. We used cold water because we thought that would be better. And we took an ice cube, put salt on it, and we took a match and put it on the salt, and we see how long it would take for it to stick onto the match. So in our bar graph right here, you can see 0 tablespoons equals 0 seconds to take that long. 1 4 tablespoons, it took about 50 seconds, and for the 1/2 tablespoon, it took about 32 seconds. And these are the materials, and my partner will explain a little more.
Okay, so I tried to get it out. She already knew how to get it out. Well, I kind of forced the ice to the side of the cup and used the match to pick it up. This is me holding it. And then I tried a little more times, which was still wrong, but she showed me after. And yeah, and these are some of the materials. We have 3 clear cups, 3 ice cubes, room temperature water, table salt, 3 wooden matches, measuring spoon, 1/4 teaspoon, stopwatch or timer, and paper towel.
And the materials we use, it shows iodized salt here, but we ended up actually using rock salt, as you can see in this photo. It's really hard to see because of the 5, but there is a different type of salt because the iodized salt was not working as well as the rock salt would, and this is our project.
Would you still eat it? The 5-second rule. Our purpose of our science experiment was to test if the 5-second rule really works. We tested strawberries falling on 3 different surfaces, along with a control strawberry, which we did not drop. We wanted to figure out which strawberry would collect the most bacteria. Would the different surfaces make a difference in the amount of bacteria that grew?
Our hypothesis is that the strawberry that we dropped outside would collect the most bacteria, while the strawberry that we dropped on the garage floor would have the second most bacteria. Then the strawberry that we dropped on the kitchen floor would have the third most bacteria. Lastly, the strawberry that we didn't drop, the control, would have the least amount of bacteria.
Materials. The materials we used were strawberries, cotton swabs, bacteria plates, and heat to make bacteria grow.
Our procedure. Our first step to
to our procedure was to drop the strawberry for 5 seconds on the floor. Then after 5 seconds, we picked up the strawberry and swabbed it with cotton swabs. After we swabbed the strawberry with cotton swabs, After we swabbed the strawberry, we spread it in the bacteria plate. Finally, we did that same procedure for the other 2 spots, the garage and the outside.
This is our graph. So control had the least amount. It had a low amount of bacteria. The garage had a very high amount of bacteria. The kitchen had a medium amount of bacteria, and outside had a high amount of bacteria. The results were, after 4 days, the strawberry that we dropped in the garage had the most bacteria. The strawberry that we dropped outside had the second most bacteria. The strawberry that we dropped in the kitchen had less bacteria. And the garage and outside strawberries, the control strawberry, the one that we did not drop anywhere, had the lowest amount of bacteria.
Our conclusion. In conclusion, we were surprised that our hypothesis was wrong. We thought that the strawberry that dropped outside would have the most bacteria, but the strawberry that was dropped in the garage floor had the most bacteria, and the strawberry that we dropped outside had the second most bacteria. Clearly, we do not recommend eating any dropped food off a kitchen, sidewalk, especially a carpet garage floor.
We also have our bacteria plates here in all of our pictures. The day 1, the day 2, the day 3, and the day 4 bacteria plates, and then we have all the pictures of the garage, outside, kitchen, and yeah.
Thank you.
The title of my project is How Hot Can It Get? So my phenomena was, if metals are placed in different types of liquids, will the thermal conductivity stay the same? My hypothesis was that the thermal conductivity will not stay the same because different types of liquids have different minerals and particles in them, which could affect the thermal conductivity. Some things about the metals are copper is used for electrical wires, kitchen utensils, machinery, and a lot of things more. Aluminum is used for kitchen utensils, packaging, aluminum foil, and much more. Iron is used for kitchen utensils, construction pipes, and many things more. Tin is used for batteries, can mix in other metals, food packaging, and much more. So, the materials I used were metals, copper, tin, aluminum, and iron. The liquids, we need liquids, filtered water, non-filtered water, peanut oil, and unsalted butter, a porcelain container, and digital thermometer. The procedure was take one liquid and heat it up to 110 degrees Celsius to 100 degrees Celsius to 110 degrees Celsius and pour them into a porcelain container that has the metals in them. Leave the liquid and the metals in the container for 1 minute. Put the thermometer on top of the metals one by one and record the temperature. Repeat this procedure for all the liquids. The results were for filtered water that copper was the hottest, it was 64 degrees Celsius. Aluminum was the second hottest, it was 62 degrees Celsius. Iron was the least hottest, which was 56 degrees Celsius. And tin was 58 degrees Celsius, which was the third hottest. For non-filtered water, copper was still the hottest. It was 58 degrees Celsius. 54 degrees Celsius. For aluminum, it was 54 degrees Celsius. Iron was still the least hottest, 50 degrees Celsius, and tin was 52 degrees Celsius. For butter, copper was the second hottest. For butter, copper was the second hottest, which was 48 degrees Celsius. Aluminum was the hottest, 49 degrees Celsius. Iron was the was the third hottest, which was 45 degrees Celsius, and tin was the least hottest, 43 degrees Celsius. For peanut oil, copper was the hottest, 70 degrees Celsius. Aluminum was the second hottest, 66 degrees Celsius. Iron was the least hottest, 49 degrees Celsius, and tin was the third hottest. So in conclusion, the pattern remains the same for filtered water, non-filtered water, and peanut oil. Copper was the hottest, aluminum was the second hottest, tin was the third hottest, and iron was the least hottest. But for butter, copper was the second hottest, aluminum was the hottest, iron was the third hottest, and tin was the least hottest. And the thermal conductivity for each metal using different liquids did not stay the same because of its different boiling points, and most probably because of the different things they have in them. So, in conclusion, my hypothesis was correct.
What type of soda makes the biggest reaction when Mentos candy is dropped into a hypothesis? I thought diet soda would make the biggest explosion because I heard it has more combination and different ingredients than regular soda. I put bottles into a large Doorlight because the weather outside was very bad. I placed a towel under the bin to try and soak up the mess. I opened the bottle of soda and immediately dropped in 6 Mentos. I measured how many high the soda sprayed into the air. I repeated the experiment 3 more times. I recorded my results and compared them. 1 bottle of Diet Pepsi, 1 bottle of Orange Crush, 1 bottle of ginger ale, 1 bottle of 7-Up, 24 Mentos, measuring tape, large store bin, towel. Why does combination Mentos and soda cause an eruption? The reaction between Mentos and soda is not a chemical reaction. It is a physical reaction caused by carbon dioxide gas from the soda combining with the surface of Mentos. Mentos candy appears smooth, but they actually have a porous surface filled with tiny holes. When Mentos are dropped to the soda, thousands of bubbles form on those tiny bumps. Similarities. This process is called nucleation. Diet soda usually creates a bigger explosion because diet sodas are far sweeteners instead of sugar, which lowers the surface tension. Lower surface tension makes it easier for bubbles to form quickly. More bubbles forming at once means more gas escaping at the same time. This pushes the soda out of the bottle upward like a tall fountain. Results: the diet soda made the biggest reaction and sprayed the highest in heat air at 16 inches above the soda bottle, 28 inches above the ground.
So, first we thought that the apple would have the most bacteria because it's kind of like wet and it would attract more germs.
Okay. All materials were like apples, Pilot's Booty, chocolate pretzel. We had a cotton swab, bacteria plates. Heat to help the bacteria grow. Experiment was placed near boil.
And then the purpose of our experiment was to see how much bacteria grows on various food items when they are dropped, fall on the floor. Our producer was first we swabbed the controlled apple, controlled pirate's booty, and controlled chocolate pretzel, and spread each sample onto the bacteria plates. Next, we dropped the apple, pirate's booty, and chocolate pencil onto the floor, and then we swabbed each one to spread the contaminated samples on the bacteria plates. This helped us compare the bacteria growth of the control sample, from food items that were dropped on the floor.
Conclusion.
In conclusion, after a full-day observation of the samples, the apple that was dropped on the floor grew the most bacteria by far. The chocolate pretzel had the second most bacteria. The pirate's booty grew the least amount of bacteria. This is a good reminder to not eat any food that falls on the floor.
So eventually it does not work.
Yeah.
Lining up.
That's what we, and those are,
Pirate's booty, and then control apple.
and those are like,
pretzel.
those are the days.
Yeah.
that
Then pirate's booty, 4 apple, 4 chocolate pretzel.
So my project is about sticking ice. So materials are ice cube, piece of string, and salt. Here are materials. And then put the ice on top, and then add a string. And then if you put salt on, then it sticks together. So when you put salt on top of the string, then the salt lowers the melting point of ice, so it slightly melts, like very little, but then it freezes again, which causes it to the string like go in like where it melted, and then freezes again, and then it sticks together. Yeah. So what I did was plate on, and then the ice cube, and then string, salt on, and then just wait. And then if you pull it, it just sticks together. That's it.
Hi. So this is our project, the eruption, and we made it so there was a volcano-like eruption by making the volcano out of foil, tinfoil clay, a water bottle to put the tinfoil on, and then we painted it black, brown, and red with acrylic paint. We used a foam board so the liquid wouldn't go out of it, and then we added a cup of baking soda, and then we added several drops of red food dye so it gets the color of the lava, and then we added dish soap, 1 tablespoon of dish soap into the volcano, then added hot water to the baking soda and soap, and then lastly we added the vinegar, and it got an eruption, and it was really cool. Our conclusion was we really wanted to get a volcano-like eruption. This occurred when the baking soda and dish soap mixture reacted due to the particles expanding after vinegar was added. This reaction caused a foamy liquid to pour out of the top of the volcano and down the sides, giving the volcano a more realistic appearance.
Hypotheses. If you add baking soda to vinegar, there will be a chemical reaction, creating foam and liquid to erupt from the top of the volcano. Here's our research. If you change the ingredients, will the volcano still erupt? How did the volcano erupt? After the volcano erupted, why did it look realistic? Would the height of the volcano affect the eruption?
Then this is our diagram. This is the vent, the ashes clouds, the throat for the lava to come out. Lava flows down. The crater, the slide vent, branch pipe, still conduct pipe, crust, magma chamber, layers of solid lava. And that's it.
Our project we did was the disappearing Oreo. The scientific question was, how long does it take for an Oreo cookie to disappear in milk?
The experiment. We decided to use 2% milk and also soy milk. We dropped the cookies in the milks at the same time and waited. Both milks had a temperature of 45 Fahrenheit.
After 5 minutes of being in the milk, we noticed that the cookie in the 2% milk started to sink. Then at 6 minutes and 10 seconds, that cookie sunk completely. The cookie in the soy milk stayed at the top. By 9 minutes, the cookie in the 2% milk started to melt. At 12 minutes, the cookie in the 2% milk disappeared. Only the cream was left. After 1 hour, there was still no change for the cookie in the soy milk.
Conclusion. Oreos disappear in regular milk and not in soy milk. Why? Cow's milk has lactose and proteins that can break down cookies. Plant-based milks cannot do that.
Our question was to see if a laser can reflect against 5 various objects you can find in your home. Our materials was a mirror, a cheese grater, sunglasses and reading glasses, and a TV screen.
So the results were, it did reflect off of the mirror, it did reflect off the cheese grater, and it also reflected off the sunglasses, but it did not reflect off of the reading glasses or the TV screen.
I think. Oh, Hunter, say the fun fact.
Oh, a fun fact is, did you know that if you point a laser pointed at the ground, you may just see a dot, but the dot is actually an invisible line?
Another fun fact is that laser stands for light amplification by the stimulated emission of radiation. I think that's it.
Thank you.
The name of our project is Baking Soda versus Baking Powder. And our question was, what is the effect of baking soda versus baking powder when baking chocolate chip cookies? My hypothesis was, I think that cookies with baking powder will not rise as much as the cookies with baking soda. Also, there might be a vast difference in the taste.
I think the cookies with baking soda will rise more than the cookies with baking powder. In addition, I believe that the taste at the two cookies will be very similar.
The acid we used in our cookies was brown sugar. Baking soda is a pure, strong ingredient that needs an acid to work, creating an instant fast fizz for recipes like cookies. Baking powder is a pre-mixed blend of baking soda and acid, creating a slower double-acting agent.
For the baking soda, the chocolate was gooey. They were salty and sweet. They were crunchy on the outside but soft in the inside. For the baking powder, they were firm and stayed in a clump. They had a salty aftertaste they had a lighter color.
In conclusion, there is a difference between baking soda and baking powder when baking chocolate chip cookies. They are not interchangeable. They have differences in appearance, texture, and taste.
This is our instant snow project, and so what we did was we put the same amount of instant snow, oh my god, and the same amount of water in each of them, and our hypothesis was that the carbonated drinks would have a similar reaction to the control than the less carbonated drinks. So in this instant snow powder that we use, there's the chemical sodium polyacrylate. That's the chemical you find in diapers, which soaks up the liquid. But basically, when you pour liquid into the instant snow powder, the sodium polyacrylate reacts with the powder and expands into snow.
And we use like different kinds of drinks, like we did like carbonation, without carbonation, with like milk. And we made it a fair test to make all of our things. So like, yeah.
And so first we put the same amount of instant snow in each cup, and then we put the same amount of water inside the instant snow. And what happened was with the control, which was the water, it grew up to, it was high. It almost like overflowed the cup. But so was the carbonated waters. The carbonated drinks, they were closer to the control, and the less carbonated drinks were like shorter, and they didn't get high.
And like our results were correct that our carbonated drinks had a more similar reaction to the control.
In conclusion, our hypothesis was correct, and the drinks with carbonation did have a different reaction than the drinks without carbonation, resulting in more expansion for the drinks with carbonation.
Yeah.
The Great Slime Experiment.
How our project worked. First, we made a regular slime, then we made slimes but replaced the glue for these materials: cornstarch, lotion, and hair gel.
I think that the slime with the hair gel will work the best.
I also think that the hair gel would work the best.
I thought that the slime made with hair gel would not work the best. I thought it would work the least because hair gel hardens. I think that the slime with the lotion will work the best because of the texture.
Our regular slime contained glue, baking soda, activator, and beads. Our hair gel contained hair gel, baking soda, activator, and beads. Lotion also contained lotion, baking soda, activator, and beads. Cornstarch contained cornstarch and the same ingredients: baking soda, activator, and beads.
Now time for the data.
We rated the cornstarch slime a 70 out of 100. We thought that one didn't work as well, but it still works the best out of all of them.
We rated the hair gel a 30 out of 100 because with the hair gel, it got so sticky that we couldn't really get it off our hands anymore.
For the lotion, we rated it out of 20 out of 100 because it was very liquidy and watery. For the OG, we rated it a 80 out of... In conclusion, we tested 3 and only got 1 to work. Only cornstarch replaced the glue.
Thank you for listening
to our
slime experience.
So we made this project together. This is my friend Skylar, and I'm her friend Chloe. And we made this project. and the title's The Slime Volcano because we both really like making slime, but we wanted to be included with the science fair, so we make some things. And this is the purpose, experiment, and conclusion. And we wrote these things here and things here, and so we first did many studies and then put our studies and write them down.
So if you want me to explain and Chloe explain the stuff. Okay, so Chloe, you.
The purpose, experiment, conclusion. But what we're trying to find out if vinegar or baking soda will make a bigger chemical reaction. The tools we use are a glass jar, baking soda, vinegar, ruler, measuring cup, slime, and food coloring. And this is just a picture of what the slime looks like when we mixed it. Step 1. First, we made the slime with 2 fluid ounces of glue, half a tablespoon of activator, and 2 pumps of shaving cream. And then we added 3 tablespoons of baking soda. Next, we put the baking soda slime in a jar. Then we measured the vinegar with a tablespoon and poured it into the glass jar. We measured the chemical reaction and did it over and over again, but increasing the amount of vinegar each time. And this is step 2. First, we put 2 fluid ounces of glue, and second, we used a tablespoon of activator. Third, we put 2 pumps of shaving cream, and fourth, we used a tablespoon of baking soda and mixed it with the slime. Fifth, we added the 3 tablespoons of vinegar. Sixth, we measured how high the bubbles went up with a ruler. And then this is just how our calculation. This is the baking soda we used, and the vinegar was our variable, which the one got higher and higher, so we made this one higher each time. This is the slime, same thing every time, and this is the height. We measured the ruler. So this is the 10th one, the highest one that we got, and it says right here, highest 10 centimeters, and that's right here.
For down here, the variable would be baking soda, and the vinegar just stayed the same. The baking soda went up each time, as you can see. Slime stayed the same, because if it didn't, it wouldn't be really a good slime for both of them. Height, it went up high and high, and our highest for baking soda was 8 centimeters. Our conclusion. Our prediction was incorrect. We thought we needed equal amounts of baking soda and vinegar. However, after all our testings, the vinegar made a bigger reaction. Therefore, we were wrong because we needed more vinegar than baking soda. The vinegar made a bigger chemical reaction because when we used 8 tablespoons of vinegar, it went up to 10 centimeters. And when we did 8 tablespoons of baking soda, it went up to 8 centimeters only. And 10 is bigger than 8.
And the reaction here, and this is the 10, this is the 8, and you can see that this is bigger. This one is bigger than this one. And then this is just, so we could see the baking soda was at
the baking soda is just
8, and the vinegar was at 10. And these are just some of our pictures, and over here was the volcano that we made out of paper mache, and it's painted, and there's a bottle to stabilize it, and we hot glued at the bottom, and there's cardboard right here, right here, right here, right here, right here, right here to stabilize it so it doesn't move. And yeah, that's our project.
So I did the water cycle. The purpose of it is it continuously circulate and purify the water in earth between the atmosphere, land, and ocean.
I know when they The materials I used are the materials in a water cycle is the water in the ocean and lakes and rivers, as well as atmospheric vapor, glaciers, and groundwater. The um the the result is the procedure is evaporation, condensation, precipitation, transpiration, and collection. Evaporation means liquid water to gas, which like the sunlight makes the water into water vapor. Condensation is gas to liquid when the water turns into water droplets. Precipitation is when the water falls down as rain, snow, sleet, or hail. And then transpiration is when the water from the ground absorbs to the roots and goes to the leaves, and the water vapor goes down. And then collection is when the water collects down to the oceans, rivers, and lakes. A conclusion is the water cycle is very important for life. We need to save water and protect nature.
Great. How would you do an experiment on this?
If I was doing an experiment, I would look like how the water is going to be evaporating, then like how it's going, like how the water is falling down.
Great. Is there anything else you think I need to know?
No.
Okay.
The questions we did were all about like, will the properties change? Will the egg bounce? And did it dissolve? And did it change colors?
Okay.
The vinegar and soda liquids cause the eggshell to dissolve. We think that the egg will turn a different color in the juice.
So, vinegar changed the egg properties the most. The eggshells became rubbery and stretchy.
You could kind of see it in this one. It kind of like dissolved when we cracked it.
Oh, wow. So that's the whole egg?
Yeah.
Well, it totally dissolved. You're right.
Water did not change the eggs. Like, it only got a little bit smaller and it had a harder shell.
Yeah.
Juice changed the color, and the corn syrup changed some of the properties. Like,
The corn syrup made it bumpy, and the inside when we cracked the corn syrup, it kind of was like stretchy. It kind of like stretched.
yeah. And only corn syrup changed the inside of the egg.
Yolk was more sticky. For the water and salt, it was thinner, and we think that because the salt kind of like mixed in with the egg.
Okay.
And also the water and sugar got the egg with some blue spots, and also the vinegar made it very, very squishy, and it kind of popped on like a water balloon.
And we just found out today that the eggshell from the Sprite is like yellow.
And the conclusion is that the first question when we asked will the properties change, all the liquids except for the juice changed some of the egg properties.
Okay.
You can see from here that all of them did it except for the juice. The question 2 when we asked will it bounce, only soaking the egg in vinegar caused it to bounce on the table. Yeah, everything else cracked. Well, we didn't really try on the table, but we knew it was going to crack.
Yeah.
You could also see from this picture when
One of them did crack, huh?
that was the vinegar.
This one was the vinegar, and the eggshell just like.
Got it.
In the question 3, the vinegar and Sprite and corn syrup and the juice caused some eggshell to dissolve. The juice kind of like made it very like cracky. So when we did it, all the eggshell got everywhere. So that's not all the eggshell.
And it changed the color since the juice we were using was like
Orangey.
Yeah.
So it soaked into the eggshell.
And then our last question, will the egg turn different colors? The juice, water plus salt, and water and sugar and Sprite caused the eggshell to change colors.
Great.
And one more thing, when we did the corn syrup, there's a bubble growing on the egg because that's how sticky the corn syrup is.
Yeah, and it was like floating, and the vinegar was like sinking with like bubbles around it.
And the water and salt one turned very foggy because the salt went raised to the top and the egg stayed to the bottom.
So how would you use this information in the real world?
We probably like do it on real eggs, like animal eggs, and see what the different eggs from animals would do on other on liquids.
Mm-hmm. Yeah, I wonder if it would be different with different kinds of animal eggs.
Yeah.
Because they might have different properties, right?
Yeah, and I just noticed it right now. Actually, the Sprite one's actually like getting a little like brown.
Yeah, look at that.
Oh yeah.
Huh. All right. Anything else I need to know?
No.
Our project
was which food makes the best fertilizer. And this project shows which food helps Blue Lake beans grow the fastest.
What we learned from doing research is that there are 3 different types of fertilizer: nitrogen, potassium, and phosphorus. All 3 of these make the perfect fertilizer combo. Out of all the foods we picked, avocado has the most potassium. Because of our research, we predicted that the cup with avocado would grow the most. It has the most potassium out of all of the food scraps. The materials that we used were Blue Lake beans, which were our plant, 8 plastic cups, and soil. We also bought regular fertilizer. The food scraps we used were pepper, kiwi, banana, avocado, apple, and orange. All the plastic cups were named kiwi, banana, apple, avocado, pepper, orange, no fertilizer, and normal fertilizer. Along with our compost cups, we had 2 variables. One with no fertilizer or compost, just soil and seeds. And the other one only had soil and normal fertilizer, and of course the seeds. We used these to compare to our cups with compost.
For the procedure, to complete our project, we planted 8 cups with soil, compost, or fertilizer. We first filled every cup a bit over halfway with normal soil. Then we put in the compost or fertilizer in each cup. We labeled each cup with what it had in it. We mixed it all up and planted 3 seeds in each cup. For the cup with no fertilizer, we only put soil and seeds. After about 3 weeks, we discovered that the cup with no fertilizer grew the most. The kiwi cup was a close second, but the avocado cup was the only cup with 2 sprouts. Here's a table with the growth of each plant.
So this is the time, and this is the plant and the growth. Apple, regular fertilizer, orange, pepper, and banana cup had no growth out of all the 3 weeks and still have no growth. However, the kiwi cup had no growth the first week, a sprout the second week, and was about 6.5 inches by the 3rd week. The no fertilizer cup had no growth the first week, a sprout the second week, and grew to about 9 inches by the 3rd week. The other cup with growth was the avocado cup. It had no growth the first week, a sprout the second week, and it had 2 sprouts by the 3rd week. One of them was 4 inches, and the other one was 3 inches.
In conclusion, the cup with no fertilizer grew the most. Even with kiwi and avocado being very close, the no fertilizer cup won at about 9 inches tall. The avocado cup grew 4 inches at most, and the kiwi cup grew 6.5 inches. Our hypotheses were incorrect, but correct at the same time, because avocado was the only cup with 2 sprouts.
Thank you.
Hi, our question is, what are the effects of different amounts of baking soda in cookies? Our hypothesis is that the cookies with more baking soda would rise higher because the baking soda makes cookies rise, and the cookies with less baking soda will be smaller. Our hypothesis is procedure is first we gathered materials for our baking. We chose a chocolate chip cookie recipe without the chocolate chips because we didn't want the chocolate chips to affect the weight or the dough of the cookie. Then we combined the ingredients. We made 3 batches, each with a different
amounts of baking soda. Batch 1 had the same amount of baking soda as the recipe. Batch 2 had twice the amount. Batch 3 had half the amount. Then we weighed the cookie dough, so each cookie had the same amount of dough. We baked 3 batches of cookies together so they all cooked for the same amount of time. After they were done cooling, we measured the width at the widest point and the height at the highest point in centimeters. We measured 5 cookies in each batch and averaged the measurements. Finally, we taste tested the cookies and described the taste of each batch. Our data was batch 1 was the same, has the same amount of baking soda as the recipe. Batch 2 had 2 times the baking soda as the recipe, and batch 3 had half the amount of baking soda as the recipe. The average width for batch 1 was 7.8 centimeters. The average width for batch 2 was 8.2 centimeters, and the average width for batch 3 was 7.8 centimeters. The average height for batch 1 was 1.0 centimeters. For batch 2, it was 1.1 centimeters, and for batch 3, it was 1.2 centimeters. The taste for batch 1 tasted like a regular chocolate chip cookies without the chocolate. For batch 2, it tasted crunchy on the outside and chewy on the inside. It was saltier than the recipe. And for batch 3, it tasted soft in the middle with a crunchy rim, and it tasted sweeter than the recipe. Conclusion. The effect of more baking soda causes the cookies to expand more while baking, making bigger cookies. Batch 2 had the greatest average width. However, the baking soda causes an unpleasant flavor that we didn't like. Therefore, bakers decide the amount of baking soda in recipes to balance the taste and size of the cookies. Our results were that batch 1 with the most baking soda had the widest cookie. We all agreed that this batch tasted the saltiest and was not as good as the recipe. We believe that the cookies rose more during cooking, but sank as they cooled. Batch 3 with the least amount of baking soda had the highest cookies. They weren't as crunchy as batch 2. They were sweeter than batch 1 and batch 2.
Hi, this is our project. Our question was, could we make a pencil levitate by using magnets? Our hypothesis was, we think that these base magnets should repel the pencil magnet so that the pencil can levitate. Our materials were a pencil, cardboard, iron ferrite magnets, rubber bands, a popsicle stick, and a glue gun with hot glue to put everything together. Our research, which is like the programs we watched for this, is physicsclassroom.com, steamit.com, instructables.com, and Sunday Science School videos. Explaining magnetic forces. Magnets have 2 opposite poles that create an invisible magnetic force field. The poles are north and south. 2 poles that are alike, like north and north, repel each other. 2 opposite poles, north and south, attract each other. Using attracting and repelling magnetic fields, we are trying to make a pencil levitate. And these are the pictures of repelling and attracting. How to create a magnet. Unmagnetized iron can become a magnet by running a magnetized object over the iron a few times, which is called magnetization. Procedure. Cut a piece of cardboard to use as a base. Cut additional pieces of cardboard to use on either side of the magnet. Use a glue gun to hot glue 4 magnets to the cardboard base. 3. Cut a popsicle stick and glue it to the cardboard base. The popsicle stick provides friction for the pencil. Hold the pencil. Use rubber bands to stabilize the magnets on the pencil. 5. Hold the pencil on top of the magnet and move it to the point where it would levitate. it needs to attract on the front end and repel on the back end. Here are some pictures of us doing the experiment. Results. When testing the base magnets repelling the pencil magnets, the pencil kept wobbling and falling. We switched the poles of the front pencil magnet to attract the base front magnet, and the pencil levitated for a second, but then it moved forward too much. Then we rested the tip of the pencil against the popsicle stick. The friction between the popsicle stick and the pencil tip kept the pencil sturdy, and it levitated in midair. Conclusion. Earnshaw's theorem states that an object cannot levitate in a stable way using only other magnets. So we thought both sets of magnets had to be repelling with no friction, but we were wrong. Then we improved our design by switching the front pencil magnet pole to attract. Next, when we fixed these features, the pencil levitated. And that's...
And we added friction too.
Yeah, with the popsicle stick.
Yeah, because it was contrary, right, to your hypothesis.
And this is it levitating. Oh. There we go.
Project is about it to see if marshmallows can cook inside can the sun cook marshmallows in a solar oven? It might take more than one day because the sun might not be out that day, but if the marshmallow cooks, my hypothesis will be right. So we put it outside for an hour. It cooked in 75-degree weather, and the sun had it to be facing, the solar oven had it to be facing the sun. I think things that I used was I used a pizza box, things to hold the marshmallows, sticks. I used tin foil, plastic food wrap, glue, duct tape, black construction paper, graham crackers, chocolate, marshmallow, a ruler, and a pencil. You can use a pen too. First, I cut out a 12 by 12 inch box into the pizza box. Then I put on the shiny side of the tin foil on top of the pizza box. Then I duct taped it around. Then I used plastic food wrap to make it a base for the oven. Then I put black construction paper inside of it so it can cook. The conclusion is the sun powerful enough to cook a marshmallow? And yes, it can.
Hi, my name is Hannah, and I made a project about catapults. And my hypothesis was, I think that both the smaller catapult and the bigger catapult would go the same distance because they're made because their motion is the same in both of them, and the materials for it were 10 popsicle sticks or 17 skewers and like other stuff like that. Both of the materials are the same on side except for the skewers. And for the actual thing, when I did it, I got, for my first test, 134 centimeters on the small catapult and 370 on my large one, and I kept on launching it for 6 times just to make sure that my my test was a fair test, and the average distance that they both traveled was 267 centimeters on the small catapult and 505 centimeters on the big catapult. I made like a bar diagram here for you to see it like this way, and then to see all the different tests I made one of these. So the results were that this bigger catapult went farther than the smaller catapult. One question I had though was if I made the catapult 3 times larger, would it go 3 times farther? Because when I launched the bigger catapult, it went 2 times as far as the smaller one. Thank you.
My name is Hudson. I created a ping pong ball snake. So my goal was to create a row of step stair ping pong balls that are hanging from a bar to swing in such a way that they look like a slithering serpent. So if you imagine a swing set at a playground, you would see a shorter or longer rope holding up a swing. The longer one would take longer to reach its normal position because it has a longer time to swing. So if you increase the length by just a tiny bit each time, then they should swing at all different times. So if you take this piece of cardboard and you put it in here, make sure they're all lined up, it should swing like a serpent. And it'll go like this for a while, going in different ways. So my conclusion was that each tiny difference in friction, speed, or even the knots holding them together will change the way the serpent slithers. So I was able to create this, and yeah, that's pretty much it.
Oh, okay, so this is our project, Survive or Die Plants Edition. Will plants survive in any other household liquids? So the purpose is we wanted to see if there's any other household liquids that plants can grow in besides water.
Hypothesis. We think seltzer will be most beneficial because it's close to water and it has carbon dioxide bubbles.
Our materials were 6 plant cuttings, and the type of plant was Scheffera. Test tubes, we got a test tube and a holder. We got measuring tape. And the liquids to test were
cold water, seltzer, milk, Gatorade, fruit punch, and olive oil.
The process is first we cut the plants about the same size and measured them. We also counted their leaves.
Then we put the liquids in the tubes.
Then we put the plants in the tubes and waited for 2 weeks.
Then we took the plants out and measured them again. We counted their leaves again.
We took notes and observed the cuttings and took pictures. So this is our data. It's kind of hard to read, but we explained it on the side. Our conclusion, we'll read that at the end. The starting height in inches was cold water was 5.25 inches.
Seltzer was 4.50 inches.
Fruit punch was 5.25 inches.
Milk was 5.50 inches.
Gatorade was 4.25 inches.
And olive oil was 4.25 inches too.
That was all before the 2 weeks. After the 2 weeks, cold water was 5.80 inches.
Seltzer was 4.70.
Fruit punch was 5.50.
Milk is 5.65 inches.
Gatorade was 4.50.
Olive oil was 4.25 inches.
Again, olive oil stayed the same. All right, then we have our pictures.
This is fruit punch after 2 weeks, and it's tall but still has mold. As you can see, this thing that we circled is mold on the plant.
Then
this is milk. After 2 weeks, the stem got skinny and a little black. Also, the milk got very, very, very chunky.
For olive oil, the height didn't change at all, and a brown spot is at the stem's bottom. And for cold water, the cold water grew by 0.55 inches and obviously did the best. It's perfectly healthy. These are the plants all together, right here. All right, and then for the bottom, this is olive oil before 2 weeks. This is it after. This is fruit punch before 2 weeks. This is after.
We didn't take that many photos of the before? So that's all we have?
Yes.
Okay.
All right, and then you explain the pictures. This is
Okay, so this is seltzer after 2 weeks, and this is Gatorade, and there's little
black
specks, dots, and the Gatorade juice got lower than it was in the beginning, as you can see in this picture. It was above the thing.
Well, after 2 weeks, no plants died. Some were unhealthy but didn't die in 2 weeks. Don't listen to the title because all of them survived. Then we have our conclusion. Let's say this together. Conclusion.
From the data, we can see that the plant in cold water is the healthiest and grew the most. The other liquid that closest to water were the next best thing. Out of 6 liquids we tested, water was the best for plants.
So none of them beat water, but some of them came really close.
Yes.
That's it. Thank you.
This is Magical Rainbow Rain Cloud by Gianna
and Giovanni.
So, introduction. Have you ever looked up at a big fluffy cloud and wondered how it holds so much rain? And what causes water to be released? When it gets too heavy, it has to fall down to the earth as rain. In this experiment, we will explore the properties of condensation, cloud formation, and precipitation. Water falling from the sky, from the clouds. By using shaving cream to represent a cloud, and colored water to represent moisture, we will be able to visualize the moment a cloud becomes saturated and releases rain into our earth.
Our materials are 1 large clear jar, 1 can of shaving foam cream, tap water, liquid food coloring, assorted colors, 6 small bowls or cups, 1 eyedropper, and 1 straw.
Our hypothesis: if colored water is added to foam shaving cream cloud, then the cloud will become saturated and heavy, causing gravity to pull the colors down through the cloud and rain into our water below.
Of variables. There are different types of variables in this experiment as seen below. Independent variables, what we change. The amount of colored water added to the cloud, the thickness of shaving cream, which was our cloud. Dependent variables. The speed at which the rain fell through the cloud and the speed which it mixed with the water below. Controlled variables. The type of jar, the amount of water in the jar, the temperature of the water, and the type of food coloring used.
Our data. Rainbow rain observation table. The red was the first one we added, and we added 10 drops. No immediate change. Orange was the second, 10 drops. It was starting to get heavy. Yellow, third, 10 drop. Red starts to come down. Green, fourth, 10 drops. Orange starts to rain down. Blue, fifth, 10 drops. Yellow and green starts to rain down. And lastly, purple, which is sixth, 10 drops. Blue and purple start to rain down.
Our procedure. Fill a large clear jar about 3/4 of the way up with warm tap water. Spray a generous layer of foam shaving cream on the top of the water, leaving some space at the top of the jar. 3. Using a straw to mix a few drops of food coloring with a little water in a small cup. Use separate cups for each color. 6.
six cups. Make sure to rinse the straw before using each color.
Results. This experiment results in colored water raining down from a layer of shaving cream, the cloud, into a clear water below, the sky, creating a swirling rainbow effect. This demonstrates the concept of participation in the water cycle. At first, the shaving cream cloud absorbs the drops of water and nothing falls through immediately. As more water is added to the cloud, the cloud starts to become heavy and the water will rain down. The different colors of water fall at slightly different times and different states, creating distant swirling streams of color to mix in the clear water below.
Back to procedure. 4. Use an eyedropper to take the colored water and gently add the shaving cream cloud. 5. Repeat step 4 for each color. Make sure to rinse the eyedropper before adding a new colored cloud to the water. 6. Observe what happens as the shaving cream becomes saturated, filled with the colored water. Eventually, it will become too heavy, and the colors will begin to fall through the jar, creating a rain effect.
In conclusion, this experiment demonstrates how rain forms in our atmosphere. It explains the concept of precipitation and the water cycle, specifically how clouds become saturated and release rain. The water in the jar represents the atmosphere or air. The shaving cream acts as a cloud, which is a collection of tiny water droplets in the sky. It is initially act as additional moisture accumulating in the cloud. As more water is added to the cloud becomes heavy and has to rain down through the shaving cream and into the clear water below. The colored water falls into the jar, representing precipitation, rain. Do you want to read the last? In real clouds.
In real clouds, water droplets gather until they become too heavy and gravity pulls them down from Earth. In summary, this experiment provides a visual representation of the Earth's water cycle where water gathers in clouds and falls as rain when the clouds can no longer hold the moisture.
This was our process of making our rain cloud, and then this was the process of when the rain cloud became too heavy and the rainbow water had to come down. Thank you for listening.
Hello, today we have Yummy Gummy Bear Lab. What we did is we put gummy bears in different types of liquids, and when we did, we waited a day or two, and we see how the gummy bear expanded.
The hypothesis is that all the gummy bears would change in size after placing them in different liquids for 24 hours, because liquid would move into and out of the gummy bear. We believe that the gummy bear soaking in plain water will grow the most because water can move into it easily.
Our osmosis is water moving from a high place of concentration and to a low area of low concentration.
The biggest gummy bear that we had was the water, because the water moved into the gummy bear, and the smallest one that we have was the juice because the smallest because water can go in and out of it.
This is a helpful use because it'll show you what types of liquids. It'll show you what types of liquids it can go. What type of liquids will be good to expand, and what type of liquids will not be good to expand.
The water was 4 centimeters, the milk was 3 centimeters, the water and sugar was 3.8 centimeters, the water and baking soda was 2.8 centimeters, the vinegar was 3.1 centimeters, the Sprite was 3.2 centimeters, and the juice was 2.5 centimeters.
That's it.
Thank you.
All right, let's hear it. What did you learn? Cars versus friction.
So basically what we did was we made a ramp using a wood, a chair, and a board. And then we had so we had more wood at the bottom. Then we put different materials on the wood at the bottom. And then we put cars down the ramp to see which one could go the farthest through the pieces of wood. And we did a control, tissue, mush banana, sand, and soapy water.
All right. So let's hear it. Your control had nothing on the wood, right?
Nothing on the wood, just regular wood.
All right. And what did you find out with the tissue, mush banana, sand? You want to tell us, Luca?
Sure. After we all did the hypothesis and the results, we were all correct that the soap made had the least friction, and none of us were correct that the mush banana had the least most friction.
Okay. So what did you think at first? Go ahead.
We all thought the soap would had the least friction. I thought the tissues would have the most friction, and they thought the sand would have the most friction.
So you thought the sand?
Yes.
All right. And what kind of car did you use? A Matchbox car?
A Hot Wheels Ford Fiesta.
Ford Fiesta. And you used the same car throughout the entire project?
Yes, same exact car.
This looks kind of messy, huh? Did you have fun?
Yes.
You had a good time doing this? All right. So what will you do when you go out riding your own go-karts? Will you ride on mush banana, or you're gonna ride on?
I'll only ride on banana for playing Mario Kart.
Okay. Where did you get this inspiration? Do you play outside with the cars?
I'm very competitive in Mario Kart. We just
We were talking about it, what we're gonna do. So, and then we just kind of led to thinking of that. And then
they were talking about friction would be a good idea.
And then we just made this idea, and
So if you all
Looks great. Looks like you put a lot of work into this. What is friction? What did you learn about friction?
So basically, friction is if something were to go on top of friction, how quickly it could stop something, or how far something could keep going.
So let me ask you this: if you have more friction, will your car go faster or slower? Okay. Excellent. So, you want to talk about your data?
so the control, the common of all three trials that we did was 34.7. All the distances together was 45.1, 30.1, and 33.5 inches. For the tissue, the common of all those was
17.333. It keeps going.
no, it was 17.4, I think.
17.333.
So when you say you have three controls, what did you do here? You had one car.
Three tests.
3 different tests?
And then we found the common between all three of them.
Okay.
And then take it from
Okay. Anything else you want to tell me?
So for the mush bananas, we each went and we got 6, 4, and 7.5 inches, and our common was 5 and 8.8 inches. For sand, we had 14, 18, and 12, and 12.75. And our common was 14.25. And then for soapy water, we had 18.25, 16, and 16.45. And our common was 16.4, right?
Yeah.
All right.
So this is Squishy Experiment by Harlow M.
Maya B.
And Peyton N. So the before, these were the before pictures of when we put them in the cups, and the vinegar, the 4-ounce vinegar, 3-ounce vinegar and 1-ounce water, 2-ounce vinegar and 2-ounce water, and 1-ounce vinegar and 3-ounce water. And then these were the after parts of what happened during the experiment. And number 3, something happened. So yeah.
Our experiment was submerging one egg in 4 ounces of vinegar, submerging another egg in 3 ounces vinegar, 1 ounce water, submerging one more egg 3 in 2 ounces vinegar and 2 ounces water, and submerging egg number 4 in 1 ounce of vinegar and 3 ounces of water. We waited 24 to 72 hours and bubbles formed, and then we removed and gently rinsed the eggs.
Our hypothesis was we think that the more the water increases, the less bouncy and squishy the egg will be. And then our materials were eggs, vinegar, tripod board, stick-on letters, colorful paper, cups, glue, pictures, and water.
Within 15 minutes, the eggs with the most vinegar began floating in the liquid. After another 15 minutes, the eggs began to fizz, and within an hour, all the eggs were floating and bubbling. 2 hours later, the eggs were still fizzing, and some of them were foaming.
And then our result was, yes, our hypothesis was correct. Egg number 1 was very squishy, but there was still a little bit of shell on it. And then egg 2 was pretty squishy, but it had a papery feeling to it. Egg number 3 was like a normal egg, but it was really fragile, so it cracked when we were rinsing it. And then just egg number 4 was like a normal egg too, but it had some weird debris on the shell.
As you can see, we redid the experiment, but only with 1 egg. These are not the actual eggs we used. These are just samples. So this is a normal egg, and this is the egg that was in 4 ounces of vinegar. That's it. Thank you.
On my science project here, I did the respiratory system. The category is engineering and design. So it took me about 2 weeks to make. And what I did is I went to Staples with my dad, and I got this poster here. I got this little bottle, the balloons, and the straw. And on a website named Canva, I typed these 4 things about the respiratory system. And same with this. I didn't make this picture, but I found it on Google. And my mom, she printed them out for me. And on my tablet, I drew these things about, related to the respiratory system. So I'm going to read this one, how I got the idea. So my mom, she's an NP, a nurse practitioner, and she talks about the respiratory system a lot with her students, which inspired me or fascinated me. And it is also a really, really important system in the human body. And what are the main parts of the respiratory system? So the main parts of the respiratory system are nose and mouth, pharynx, larynx, trachea, bronchi, lungs, bronchioles, alveoli, and diaphragm. So the nose and mouth are the primary entrance. The nose and mouth are the primary entrances for air. The nose is lined with tiny hairs called cilia that filters out dust and dirt. Pharynx is actually the throat, a tube that connects the nose and mouth to a windpipe. Larynx, it's a voice box. Located at the top of the windpipe, it contains vocal cords that vibrate to create sound when air passes through. Trachea, windpipe, the main tube that carries air down into the chest. It is held open by stiff rings. Bronchi, the trachea splits into two large tubes called the bronchi, one for each lung. Lungs, two main organs in the respiratory system. They're spongy and protected by the rib cage. Bronchioles, smaller branches of tubes inside the lungs that look like branches of a tree, like these. Alveoli, tiny air sacs at the end of each bronchioles where oxygen enters the blood and carbon dioxide leaves it. Last one, diaphragm. A large dome-shaped muscle located under the lungs. It is moved down to pull air and push air out. So, this one. What are things to do to keep your respiratory system healthy and strong? This one is also a really important paper. So, you have to stay active, which means you can play sports, ride your bike, take a hike, or even dance. You have to eat. You have to eat healthy foods like carrots, bananas, broccoli, strawberries, any of fruits or vegetables. You have to drink lots of water and milk too. Not a lot of milk, but like you have to drink milk because that gives you strength about your respiratory system, and drink lots of water too. And also when you sneeze or cough, you have to cover your you have to cover your mouth so you don't spread germs. And once you use the bathroom or coughed, sneezed, you have to wash your hands for about 30 seconds or a minute. And yeah. And so here, fun facts. Your lungs are like sponges that fill your chest. To the left one is smaller for your heart. They can float on water, and they have tiny air sacs, alveoli, the size of a tennis court, spread out, helping you breathe in oxygen and get rid of carbon dioxide with tiny hairs in your nose, cleaning the air. You take about 7,000 breaths a day, mostly without even thinking about it, and even yawn to get more oxygen. And these are some pictures here that I found on Google. It's a diagram of the respiratory system. This one's the respiratory system, respiratory system, respiratory system. It's just the same thing, what I listed here, but just with pictures. And here, I builded a model of the respiratory system. So it says my name here, respiratory system, 4cc, and the respiratory system. So what you do is when you breathe like this, so you start off with no air here. So this, you can see there's no air in this balloon. But when you breathe, it fills air. So that's kind of how the respiratory system works. And this is a really important quote someone made. I don't really know who, but I found it on Google. It says, "Lungs help us breathe in oxygen and breathe out carbon dioxide." Thank you. Bye.
So I and the two colleagues had the privilege of judging today's contest, and I got to tell you, the students were fantastic. They were enthusiastic, they were excited, they learned a lot, they were really happy to talk about their experiments and what they came up with. And I think what was most fun for me is they all understood that a wrong hypothesis is not bad. That hypothesis is learning more and gaining more data to do the next thing. So even if their experiment didn't go the way they thought it should, they still learned a lot. So they were fantastic. We were really excited to be here, and it's wonderful to see Cottle School teaching students about the scientific method and about how they can use their own independent thinking to come up with conclusions about the world.